Velocity analysis. Velocity in mechanisms and machines can be determined using either analytical formulation or graphical constructions. This section focuses on the principle underlying graphical velocity analysis. Consider a rigid link OA rotating about a fixed point O with an angular velocity omega. Let VAO velocity of point A relative to fixed point O, VBA velocity of an intermediate point B relative to point A, VBO absolute velocity of point B relative to fixed point O, VBO is equal to VBA plus BAO. As the link undergo an infinitesimal angular displacement del theta in a time interval del t, point A travels along an arc to position A. Velocity of A relative to O, limit del t approaches to 0, arc AA dash by del t, VAO r del theta by del t, r d theta by dt is equal to r omega. Velocity of roving. The roving velocity at a pin joint connecting two surfaces depends directly on the relative angular velocity between the two interconnected links. Consider standard 4-bar mechanism considering the link AD, AB, BC and CD. Pin at joint A. Joint is fixed link AD and the moving link AB. Since the link AD is completely stationary, omega AD is equal to 0. The velocity of roving depends solely on the absolute angular velocity of AB vector VR of A R A omega AB, where R is the radius of pin A. Roving velocity joint at D fixed to moving connections. Pin at joint D joints is fixed link AD and rotating follower link CD. We rob D at D omega CD, where at D is the radius of pin D. Joint V moving to moving connection opposing rotations. Pin at joint V connects to moving link AB and BC. If link AB rotates clockwise and link BC rotates counterclockwise, anticlockwise, their relative angular velocity add up. B rob B is equal to RB omega AB plus omega BC. If both links rotate in the same directional sense, example both clockwise, the robbing velocity would be proportional to absolute difference RB omega AB minus omega BC. Moving to moving connection general gas. Point at joint C connect moving link BC and CT. BC RC omega BC plus omega CT. Theory of instantaneous center. When a plane body moves non-linearly relative to another body, its motion at any given instant can be treated as pure rotations about a specific point. This point is defined as the instantaneous center of rotations or virtual center. Suppose a plane body P moves relative to a reference body Q at a specific instant to distinct point A and B on body P possess linear velocity v and B respectively. If a line is constructed perpendicular to the direction of B at a point A, the body must be rotating about some point along this line to satisfy its current direction of motions. Similarly, a line is drawn perpendicular to BB at point B. The unique point of intersection of these two perpendicular lines is designated as the instantaneous center I. At this exact moment, body P behaves as if it is in pure rotation about I. Parallel velocity rules. Moving body center at pure translation. Parallel velocity rules. If the linear velocity v and bv are completely parallel to each other and their perpendicular lines do not intersect within a finite boundary, the instantaneous center of the body lie at infinity signify pure translational. Centroid. Because of the configuration of a mechanism shifts continuously over time, the spatial position of the instantaneous center changes. The continuous geometric locus of instantaneous center during a link motion is called centroid, a space called axode. A line passing through the eye center and oriented perpendicular to the path or plane of motion is called the instantaneous axis. The surface swept out by this axis during execution of the complete motion cycle is defined as exode. Instantaneous centers in common configurations. The location of the eye center I want to between link 1 and link 2 can be readily specified for common kinematic pairs. Turning pairs. When the two links are connected via a simple pin joint, the instantaneous center is permanently fixed at the geometric center of the pin joint. Pure rolling, sphere or cylindrical on cylinder on a plane for a body executing rolling without sleeping over a stationary surface. The instantaneous center of velocity is located exactly at the point of contact between the two bodies. At this point, relative linear velocity is zero. Mechanical dynamics, sliding conditions, and instantaneous centers. Pure sliding on a flat plane. Pure sliding on a flat plane, when an object slides linearly over a straight flat surface, the direction of motion is purely parallel to the surface. Consequently, its perpendicular lines meet at infinity. Thus, I want to lie at infinity along a line perpendicular to the sliding plane. Sliding on a curved surface. If a slider moves along a fixed curved surface, the instantaneous center is located exactly at a center of curvature of the profile at that instant. Number of instance centers. For any mechanisms comprising a collection of distinct links, the total number of instance centers representing all possible pair of links is determined using combination theory. N is equal small n whole n minus 1 by 2, where n is total number of links present in the mechanisms. Crank and slotted lever quick return mechanisms. This mechanism converts continuous rotational motion of a crank into reciprocating tools motions, featuring a slower cutting stroke and a rapid return strokes. Stroke action governance. The stroke action is governed by the cutting angle alpha and return angle beta determined by the extreme tangent positions where the crank becomes perpendicular to the slotted lever. Time of cutting stroke by time of return stroke alpha by beta 360 minus beta by beta, where the angle beta is evaluated via geometry relations of the fixed configuration cos beta by 2 evaluation. Maximum tool velocity. The linear velocity of the slider at the cutting head reaches its absolute maximum value when the slotted lever is at vertical positions. Maximum cutting velocity occurs when the crank pin is at its highest point closest to the sliding guideline. Omega r whole L by c plus r. Maximum return velocity occurs when the crank pin is at its lowest position between the fixed centers. Yes, maximum return omega r L by c minus r. Fundamental kinematics theorem. Aaron Holt Kennedy's theorem. Three centers theorem. The theorem states that if three rigid bodies undergo relative planar motion relative to one another, their total instantaneous centers of rotation must lie precisely on a straight line. For instance, considering three moving bodies designated as 1, 2, 3, the three associated instance centers I1, 2, I2, 3, I1, 3 are guaranteed to be collinear. This theorem serves as structural foundations for graphical locating hidden or unjointed centers in the complex link network. Angular velocity ratio theorem. The angular velocity ratio theorem provides a direct method to relate angular velocity of any two moving links in a mechanism relative to a common reference link. Determinations of intermediate velocity. The theorem states the angular velocity ratio of any two link relative to a third reference link is inversely proportional to the distances of their common instance center from their respective centers of rotation. For two moving links 2 and 4 moving relative to a fixed frame link 1, their common instance center is I24 according to the theorem omega 4 by omega 2 I24 minus I12 divided by I24 minus I14, where I24 minus I12 represents the physical linear distance measured between instance center I24 and I12 I24 minus 14 represents the physical linear distance measured between instance center I24 and 14.